how you imagine black holes is probably wrong, or at least very incomplete. If you're picturing some lonely void or anything resembling a vacuum cleaner, then you're missing out on some of the most fantastic things that black holes are actually capable of. If you're instead picturing something like what was depicted in Interstellar, or like on the poster behind me, you are getting warmer because those at least depict an accretion disk, or a bunch of matter orbiting the black hole and trying to fall into it. But note, even matter really close to a black hole may never actually reach it, because only the dark part is the true point of no return. Technically, all the mass of a black hole is inevitably crushed into a infinitely small space in the center called a singularity, but their mass is not infinite, therefore their gravity or their attractive force is not infinite. But then, since gravity depends on both mass and distance, we define the edge of the black hole, also known as the event horizon, as the proximity to the singularity at which the gravity does become so strong that nothing, not even light, can escape it, giving them their name. Outside the black hole, you're potentially fine because you haven't been given your one-way ticket yet. For example, that's the reason we're able to see light emitted from very close to the black hole. And sure, some of the matter will fall into the black hole and increase the black hole's mass, but what you probably don't know is that the act of matter simply trying to fall towards the black hole, aka black hole accretion, is actually the most efficient process at converting matter into energy in the universe, so much so that nuclear fission, like in an atom bomb, or nuclear fusion, like what holds up stars, is nothing compared to this. This also means that accretion onto black holes, especially supermassive ones, are actually some of the most powerful mechanisms in the universe. The consequences of this are huge, such as the fact that it's way harder to fall into a black hole than you think, because their local environments are so dramatic and chaotic, with all the matter and electromagnetic radiation outflowing in every which way. So much so that even though black hole accretion is a very efficient power source, accretion onto black holes is actually a very inefficient way for black holes to gain mass. One of the big open questions in astronomy right now is, if accretion is such a slow process, then how do we get such supermassive black holes so early in the age of the universe? And something you may be familiar with is that supermassive black holes are found at the center of most spiral-shaped galaxies. And even though supermassive black holes gravitational influence may be somewhat small compared to the even more giant and massive galaxies that they reside in, there is evidence for a major relationship between them. And this evidence, paired with what we know about black hole accretion sending matter and energy back into their galaxy, leads to another question, and one which I am right now helping study, is how do we connect these smaller scale pictures of black holes to these large scale effects we see on whole galaxies?